Technical check. Can you hear me?
Yes, I can.
Well, thank you. So I guess we can start if you are ready. Okay, good afternoon to everybody. Welcome to the CPS Explore session of the ICCSA International Conference. I want to thank the speakers for their presence, even virtual, and pass the floor to them. The first work we are presented is a comparative study of commit representations for JIT vulnerability prediction. The author is Temas Aladix. Am I correct?
Yes, I am.
Okay. Temas, are you ready to present?
Yes, can I share my screen?
Yeah, you can proceed.
I hope you can see it all right.
Okay. Well, yes, it's okay now.
Okay, thank you. Then I start now.
Yes, you can proceed. Go ahead. Thank you.
Thank you. Hello, everyone. Good afternoon. I'm Tamás Aladic, and I will be presenting you this paper called "A Comparative Study of Commit Representations for Just-in-Time Vulnerability Prediction." And I will start by some motivation, some background of the general topic that we are trying to solve here. And the main goal is detecting software vulnerabilities. This one is a really pressing issue lately, as you can see on the slide. Even though it's slightly outdated data, it's from 2020 and 2021, but it's still the same thing applies. So the appearance of vulnerabilities are on a rapid rise from 2022 to 2020 to 2021. There is a nearly 20% increase in the discovered vulnerabilities, which is a very alarming rate of increase. And also from these vulnerabilities, more than 100 were zero-day vulnerabilities, which means they could be exploited on the go. So the developers of the original software that were exposed had 0 day to fix the vulnerability. It was already exposed. So these are very pressing issues. And to a little bit more narrow down the topic that we were dived in, you can see that based on this observation that the vulnerabilities are on rapid rise and a lot of them are very pressing, we wanted to detect software vulnerabilities, but as soon as possible. And how is it done traditionally? Traditionally, it is done by using static and dynamic software analysis tools. These tools, and I'm typically talking about static analysis tools, are basically implemented by finding patterns in source code and related artifacts to find vulnerabilities, and human resources are needed to do this. The cons of this are listed as follows on the slide. So these are, as I said, have to be manually implemented. So if a new vulnerability is discovered or a new kind of bug is discovered, then a group of developers have to do the implementation of static analysis tools. And also because of this human factor, the adaptation is very slow. The industry can't really keep up with the appearance of new vulnerabilities. Thankfully, lately machine learning has got a lot of attention, mainly because of the massive data that we have available in many fields of the internet and IT. And that is also the case in software related topics, because we have a lot of online and accessible by everyone open source projects, and based on these we can train models. Since we have a lot of projects, open source projects, and we have data about if they are vulnerable or not, we can use that to train machine learning models. The other part of this goal is not just to detect vulnerabilities, but to do it as soon as possible. And when should this as soon as possible time should be? A suitable early point of the time when the source code is mature enough, but also it is not too early to add is commit time. In more detail, when we add the changed code to the code base. At this time, what is available is a commit metadata, the author and the changed lines of codes as numbers and etc. The source code, which is the changed code itself, and the commit history and other things that we can, I guess we all know from the Git and the related version control systems. So now we see that our goal is to predict software vulnerabilities as soon as possible. But how should we do that? As I have already mentioned, our aim in our paper and the industry and the scientific field is also moving towards machine learning approaches. But there is a problem that commits, as seen on the previous slide, consists many different aspects. They have metadata, they have changed lines of code, they have author informations. So it is not trivial to convert these to numerical inputs because machine learning models take numerical inputs. So the commit representation as a topic is how to represent commits that they can be understood by machine learning models or in a way that they can be fed to machine learning models, and also keeping some semantical or syntactical information. So this is the main problem. And in our paper, we try to provide some insight to this field of commit representation by comparing two different state-of-the-art methods. And we also incorporated our method that we published some years ago, like 1 year ago. And through this study, since it incorporates state-of-the-art methods, it gives some insight how well these machine learning models can work now, and also some insight into their limitations, how effective are they generally, and the rest. And what are these models that we use to compare or show the state of just-in-time vulnerability prediction at the time? The first one is called DeepJIT, which is a paper and an approach from 2019, so 4 years ago. But it achieves very good results even then. And if not, I didn't. This paper doesn't contain today's proceedings, but up to the last year, it was the state of the art, one of the state of the arts. So this DeepJIT model uses separate convolutional networks to extract features from both the commit messages and the code changes. And so we have two different convolutional networks for that. And these convolutional networks are designed in a way that they try to extract information from different levels of the input. In case of commit messages, these are structured as they have words and they have sentences, and these are different layers of the convolutional networks. For code changes, different convolutional network layers are corresponding to the hunks, to the diffs, and also the different files that are changed as part of the code change. So these convolutional networks are structured in a way to mimic the actual setup, the actual structure of the commit itself. So after they have basically extracted information from the commit message and also the code changes using these convolutional networks, the authors propose that these two representations should be aggregated using a linear layer called fusion layer. And once that is done, the output is a binary label if the set commit is vulnerable or not. The other approach that we used as state-of-the-art is 1 year after the previous one, so that's coming from 2020, and it's called CC2WEC, which stands for Code Change to WEC, and it's a general use commit representation form, so it's not tailored for vulnerability prediction. It's a general use case representation form. It can be used for many different tasks, for example, commit message prediction, or vulnerability fixing, commit finding, and etc. But anyhow, the basic architecture of this paper is can be seen on this slide. What they do is they use the very popular and basically everywhere used attention mechanism, which is used in transformers too. But here they use a specific structure based on attention called hierarchical attention networks. And here again, very similar to the last work, they try to mimic the structure of the commit itself. So using this hierarchy of files, and in the file we have changes, and the changes are made up of different diffs, and the diffs compose hunks. For each of these levels of changes, we have a layer in the, or a sub network in the hierarchical attention network. So what they do is extract code changes from each file. They, using this hierarchical attention network, they parse the commit, each part of it, and in the end they concatenate this representation to a change vector. They use many different, little bit different from the last approach. They use many different fusion layers, so they try different combinations of these vectors, and then in the end they aggregate them. And once again, the difference between the last approach and this one is that the objective of the training phase is not to predict vulnerabilities like in DeepJIT, but to predict the log messages to generate a general use representation form. And the final model that we use to compare and give insight to the vulnerability, just-in-time vulnerability prediction scene is our method, which was published like a year ago. It's called change trees based representation forms. It's actually not an entire architecture, just a way to represent source code, because as you could see in the last slides, the previous two state-of-the-art methods treat source code as natural language, basically instances of natural language. In opposed to that, we used the structure of these codes, and we use the fact that each source code has a corresponding AST to it. And for each source code, we try to present an AST that doesn't contain everything that's in the source code, but only the changes. And this tree is called change tree that we proposed. And here is some motivation how this one works. I won't go in detail how this tree is constructed, but just how does it look. So in this slide, you could see on the previous slide, there is an example of a very simple code change. And the post state, so the state on the right, you can see, we mapped it to the corresponding AST, the abstract syntax tree. And here you can see it's a large tree, even if maybe it's not so well visible on your screens. The main idea is that it is a big tree with many nodes, even if the code is very simple. On the next slide, we can see the corresponding change tree that only retains the different paths that are changed as part of the code change. And as you can see, the reduction is very big. In the paper, it is said that it's like 60% on average for each commit. So it's a substantial reduction in size, and also it discards unnecessary paths of the tree. So it is a useful representation form. And how did we compare these different methods and approaches? We used a data set that was based on a introduce a fixing commit dataset created by SAP, a German company. This dataset contained different fixing commits, and for these fixing commits, using another method, we mined a number of vulnerability contributing commits. Namely, you can see the numbers there, 474 vulnerability contributing commits that we were able to mine like this. And for each of these vulnerability contributing commits, these are our positive samples in the data set, we sampled randomly. So for each fixing commit from the same repository, we randomly choose 4 commits, saying that and taking from the observation that a randomly sampled commit is very unlikely to be vulnerably introducing. So using that fact, we label them as non-contributing, and you can see on the screen how did we what is the result. So we have this ratio of non-contributing commits and vulnerability contributing commits. Based on this data set, we trained and evaluated all of these methods. There is a baseline that was basically just a very simple model that would predict true for the same ratio as the vulnerability and non-contributing commits ratio. So since in this case that's 22%, this baseline model that you can see on the bottom predicts true for a commit with a 22% chance. This is a very simple baseline, and the rest is, as I have introduced, the DeepJIT model, the CC2X model, and the change tree based model, which is used with a random forest because the change tree is flattened using a depth retraversal to get the information from the tree, and then a random forest model is trained on it. And on the results, you can see that the best performing models are the DeepJIT models. The scores are actually measured in different F-score bases. These correspond to the different how well we incorporate precision and recall into the F-score calculation, and this can give insight how much we care about false positives and false negatives. Mainly, what we say is that in these cases, precision is the most important because developers usually don't like to look at a lot of false positive examples. Based on that, what we concluded in our paper is that these methods are still need a lot of refinement because the overall precision score is pretty low. The recall is better, but still these tools can be useful for different supplementary techniques for manual inspection at this time.
Sorry, may I invite you to go to the conclusion, please?
This is the completion. One more sentence.
Oh, okay. Thank you very much.
So
you can proceed.
Okay, so yeah, and what else? Well, I think okay, then I'm done. So this was our paper. Thank you for your attention. If you have any questions, I can answer them.
Thank you very much for your contribution. And is there anyone who has a question? I guess we don't have any questions. Oh, clear.
Okay, thank you.
Thank you very much for your contribution. Okay, we can proceed. The next work for this afternoon is an experimental study investigating the effects of data preprocessing methods on deep learning-based time series data prediction. I guess the presenter is Mustafa Bugra Yilmaz. Is it correct?
Yes, can you hear me?
Yes, I can hear clearly. You can proceed when you want.
Okay, let me share my screen.
Yeah.
Is it visible?
Yes, it is. Okay, you can
Okay,
proceed.
thank
Continue.
you. Hello, everyone. My name is Mustafa Yilmaz. In this presentation, I want to talk about our study titled An Experimental Study Investigating the Effects of Data Preprocessing Methods on Deep Learning-Based Time Series Data Prediction. Time series data is widely used across various fields like finance, economics, healthcare, transportation, and more. Predicting future time series values is useful in these fields and more. In finance, for example, predicting the future values of financial time series could be crucial for investors to make informed decisions about buying and selling stocks, bonds, and other financial instruments. These are some questions that are important in terms of this study. The first one is, what is a good machine learning algorithm for financial time series trading? Another is, can other algorithms be used as pre-processing to improve long short-term memory prediction results? And the final one is, are wavelet transform and stacked autoencoders effective in improving time series prediction performance? Here we can see the structure of the process. The structure has mainly three parts: data splitting, algorithms, and the results. As you can see, this study uses long short-term memory for the main prediction and discrete wavelet transform and stacked autoencoder as pre-processing techniques. Let's detail these modules in this study. For the training, we split the data into different windows. Data is split into sliding windows of 2 years. For each of these years, the window is split into three parts: train, validation, and test. All this data is continuous since time series data cannot be split like regular data for other machine learning tasks. For each window, train data is fed into the pre-processing methods and the main algorithm. Meanwhile, validation data is used to oversee the loss values of the algorithm. Then, after the training is done, the test data is fed into the trained algorithm and the prediction results are saved alongside the real test data. In our case, the extent of the test data is 3 months. Then we slide the window by 3 months and repeat the process, saving the results every time. Because of the way the sliding is done, as is done in this study, all the 3 months of test windows are continuous in terms of dates. Therefore, after the sliding is done, we have approximately 6 years of continuous result data. Then, with the results that we have saved, we apply a backtesting function using the real and predicted values. We again save the results of this backtesting function and do error evaluation between these values. Now, I want to talk about the technologies used in this study. The code is based on a deep learning based time series prediction code implemented by the user MLPanda on GitHub. In the base code, all of the three main and the pre-processing algorithms are used together. We have expanded the code to allow for a separation of these algorithms so that they could be compared with each other. We have also expanded the code so that the period of data that is gathered from the output of the algorithm is as described before. The language used in this study is Python. Python has a wide range of library selection and is quite easy to use. It's also widely used in the field of machine learning. There are many libraries used in this project, but the most relevant library used is PyTorch, which provides all of the deep learning methods and models in this project, like LSTM and stacked autoencoder. We use the same dataset that was provided in the GitHub repository, which is the Standard & Poor's 500 Index, or S&P 500. S&P 500 is an index that tracks the stock performance of the largest 500 companies in the United States. The data file we have used specifically has approximately 2,000 days of data and 21 features, with 19 of them possibly being relevant to the training of the model. But the target feature used is the closing price. We scale the data into appropriate ranges so that the model does not overvalue features that have much larger range of values than other ones. The first data preprocessing used in the study is discrete wavelet transform. The wavelet transform is a mathematical technique that analyzes signals in both the time and frequency domains. It uses wavelet functions to capture localized time and frequency characteristics. It can reconstruct, and deconstruct time series data, which could possibly help with feature extraction by reducing detail, as you can see in this image. The second preprocessing technique is the stacked autoencoder. A sparse autoencoder is a type of artificial neural network used for unsupervised learning and dimensionality reduction. It learns to encode high-dimensional input data into a compressed, lower-dimensional representation while enforcing sparsity, which means that only a small number of hidden units are activated for a given input. This helps extract more relevant features for the training. Stacked autoencoders use multiple sparse autoencoders back-to-back to again improve the relevancy of the features. The main algorithm that predicts the feature values of time series is long short-term memory. Long short-term memory is a type of recurrent neural network that addresses the limitations of traditional RNNs in capturing long-term dependencies in sequential data. It introduces memory cells and gating mechanisms that allow for effective information retention and selective information flow. LSTMs have proven highly successful in tasks such as natural language processing, speech recognition, and time series prediction. The way the evaluation is done in this study is by backtesting. Backtesting is a method to assess performance of a trading or investment strategy using historical data. It involves simulating the strategy on past data to evaluate its effectiveness. It can help traders refine their strategies, understand risks, and gain confidence in their performance. In this case, a buy-sell situation is simulated using the real and predicted results, and then we measure the difference between the two results. Here you can see one output of the backtest results for only using LSTM versus using all discrete wavelet transform, stacked autoencoder, and LSTM for year one. Of course, it's not very easy to understand the difference from a graph, so here's a table with the results of all algorithms for all 6 years. For the results, we measure the difference between the results with RMSE and MAPE. RMSE stands for root mean square error. It is a commonly used metric to measure the average difference between predicted values and actual values in regression analysis or machine learning models. RMSE summarizes the magnitude of the errors given a single value that represents the overall model performance. MAPE stands for mean absolute percentage error. It is a metric used to measure the accuracy of a forecasting or prediction model. MAPE calculates the average percentage difference between predicted values and actual values. It provides a relative measure of error, making it easier to interpret and compare across different datasets or models. From these results, we can see that the inclusion of SAE compared to only using LSTM reduces the average RMSE result from 0.134 to 0.04, and for MAPE, it reduces from 12.6% to 3.4%. Inclusion of discrete wavelet transform has not affected the results, whether it's used with or without SAE. Now I want to talk about the limitations of this study and the threats to the validity of the results. We only use one dataset. Since financial time series is a complex field, different datasets could give different results because of reasons like the amount of data, the features available, different markets having different characteristics, etc. Another point is that we just use long short-term memory as the main deep learning prediction technique. There are a lot more possibilities and experimental studies that can be conducted using different types of deep learning techniques to see if they're effective or not, and compare them with the results like ours. We also use only two data pre-processing methods. Like the point about the main technique, more pre-processing techniques could allow us to find more effective results or less effective. In that case, it would still be valuable feedback. And also, we use the original model parameters as is. The parameters could be changed and tweaked to see what works better or worse. It could be possible to maybe improve these results by finding more efficient parameters. For the conclusion part, the results show that the inclusion of stacked autoencoder with LSTM improves training and backtesting results. On the other hand, the wavelet transforms seem to have no effect on the results. So for the dataset and the parameters used in the study, results show that the stacked autoencoders improve the results of long short-term memory-based time series prediction and backtesting results. We could expand on this study by doing more detailed work in the future, like I stated before. Many more algorithms could be used to test the effects of data pre-processing methods. Using many more datasets could give us more information about the effectiveness of the pre-processing methods, depending on the market or the features of the dataset. Tweaking the parameters and testing different combinations could improve the results or give us an idea of which parameters make the results worse. Also, we could use different performance evaluation techniques for a more solid result set. This was my study. Thank you for listening. If you have questions, I could answer.
Thank you very much, Dr. Hilmetz. And is there anyone who has any questions for Dr. Hilmetz? No question?
Okay. Thank you so much for listening again.
Thank you so much, Dr. Hilmetz.
Thank you.
Thank you. Well, we are on time, but if the next presenter is ready, we can start. Are you ready?
Hello.
Dr. Demon, hello.
Yes,
If
I'm
you
ready.
Okay, if you are ready to present, we can proceed.
Okay, let me share
Okay.
the screen.
Okay, you go. You can go ahead. Okay, I can see your screen.
Is it seen right now too?
Yes, but you are in the presenter mode. Okay, okay.
Yes, since there are two screens, I couldn't share the other one. Just a moment.
Yeah, don't worry. We are on time. You can take your time.
Okay.
Okay, now it's perfect.
Okay.
Yes, if you want to start. Okay, thank you.
Thank you. Hello all. First, I'm Eren Duman. I am joining from Istanbul, Turkey, and I'm currently an undergraduate student at Yıldız Technical University. My research was about credit risk prediction based on psychometric test analysis. Now I'm starting the presentation. Credit risk management is a crucial concern for any organization, regardless of the circumstances, but it holds particular significance within the banking sector. It is crucial because loan default could create problems more than just financial losses. For example, this may cause banks to miss opportunities, or this could create extra transaction costs for banks. The severity of the situation becomes more apparent as financial institutions grapple with the consequences of unpaid debts. Like I said, such debts do not only affect the profitability and stability or financial situation of these institutions, but it also have broader implications for the overall economy. As unpaid debts accumulate, financial institutions may find themselves forced to write off these losses, and this in turn can weaken their ability to lend and invest, so that it could affect the whole economy. Firstly, why we use psychometric data while there are so many methods to evaluate credit risk with financial data and with high accuracy. First motivation about it is financial data is not accessible all the time, and it may have a few reasons for that. Firstly, customers' financial data may be incomplete, or institution may not have permission to access customers' financial history. And secondly, and I think this is more important and more common, young people generally do not have a financial history due to their age. For this reason, banks hesitate to lend to young people, even if they have high incomes. Using psychometric data will also help to measure the credit risk of these people. And the other motivation is to use psychometric data is to increase accuracy of credit risk prediction with financial data, because the importance of measuring credit risk has significantly increased in today's changing and evolving lending landscape. Nowadays, in addition to the traditional methods of acquiring substantial loans, smaller installment-based loans are commonly offered in retail stores. And furthermore, the utilization of credit card is steadily growing and leading to a substantial increase in the frequency of borrowing credit. And this graph shows the rate of credit card usage by some countries and years. And as you can see here, there's a general increase in credit card usage over the years. And another headline is fundamental concepts. There are three concepts: creditworthiness, psychometric test, and future vector. First, creditworthiness is about how trustworthy and reliable you are when it comes to borrowing money or managing your financial obligations. Lenders and financial institutions evaluate your creditworthiness to determine if they should lend you money or extend credit to you. And they take a look at various factors like your credit history, income level, job stability, and existing debt to assess your creditworthiness. And as I mentioned before, this study investigates whether psychometric data reflects the creditworthiness feature in addition to these features. And the other one is psychometric test. Psychometric test is a test consisting of questions that will express the creditworthiness of the person. In this study, the attributes that can express creditworthiness were examined with experts, and test questions were prepared according to these features. And these features will be discussed later in the presentation. The last one is the feature vector. A feature vector is a mathematical representation used in machine learning, computer vision, and natural language processing. It captures relevant characteristic of an object or a data point, and typically as a one-dimensional array with elements representing specific features. Feature vectors enable efficient computation and analysis by structuring complex information. And in machine learning, they serve as input for training models and making predictions. The other topic is research questions. First, we asked ourselves how much do psychometric tests contribute to credit lending decisions compared to the traditional credit assessment methods. Traditional methods have long been used to evaluate creditworthiness, but our research aimed to uncover the specific impact of psychometric tests in the context. Moving on, we explored the question, how can we analyze the behaviors that indicate a customer's creditworthiness? Understanding the behavioral patterns that signal creditworthiness is crucial for accurate lending decisions. I will showcase these behaviors and demonstrate their relevance in assessing creditworthiness. And lastly, we investigate the question that how can a customer's credit risk be predicted based on future vectors, and what machine learning algorithms can be used for this purpose. By leveraging future vectors and machine learning algorithms, we sought to develop a predictive model for credit risk assessment. We will present our research methodology and highlight the machine learning algorithms we used. You can see the representation of the methodology in this figure. And first I want to start with the data preprocessing module. The raw survey data is a CSV file containing people's answers to survey questions and labels indicating their credit risk. In order to be used as an input for machine learning algorithms, the dataset need to be transformed to array of feature vectors, and this is done in data preprocessing module. Target encoding method was also used in data preprocessing section. Target encoding is an effective encoding technique of categorical variables, and it's often used in machine learning algorithms for processing tabular datasets with a mixed number of numerical and categorical variables. And there's an example of target encoding in this figure. As you can see, animal names are encoded as numbers in this figure. The dataset used in this study consists of 18 item questionnaire, and the raw data is in form of a text file containing questions and their corresponding answers. After preprocessing, the data is transformed into a tabular format with 18 columns, and where each column represents respective questions answers. And I want to continue with model construction and prediction module. In the model construction module, 5 different algorithms were used, like KNN, SVM, logistic regression, decision tree, and random forest. These 5 different algorithms were tested on the dataset, and the results were compared to determine algorithms suitable for the dataset. In the design application, one of these 5 algorithms can be selected via the interface. By selecting one of the algorithm, training can be done, and training results can be observed in the interface. And the last module is the prediction module. In the design application, there is a section that contains psychometric test questions, and the model trained in the previous module, and model construction module, and the module used in this step, prediction module. A future vector is created from answers of the customer who solved the questionnaire, and then this used as input to the model to predict credit risk of that customer. Python language was preferred in the study due to its easy readability and the presence of many libraries in it. The library that hosts a machine learning algorithm is a scikit-learn library, and the library used to design the interface is PyQt5. And in addition, libraries such as NumPy and CSV was also used in the study. The dataset consists of the survey responses of approximately 100 individuals and their credit risk. While creating the dataset, subjects were interviewed, and the labels were created by estimating the credit risk of the subjects. In this study, binary labeling was used. Individuals' credit risk can be high or can be low. Since there are 18 questions, there are 18 columns in the dataset, and the survey is a Likert scale survey. There are 5 answers ranging from strongly disagree to strongly agree. Each question in the dataset is mapped to an attribute, and these attributes are the features that express the creditworthiness of a person. You can see some of these attributes here, and I will explain some of them. For example, responsibility and ability to fulfill financial commitments affects on individuals' creditworthiness. Responsible people usually pay their loan debts regularly, and they stick to their financial commitments. Therefore, responsible person may demonstrate a higher creditworthiness, while low responsibility may increase the credit risk. And the other feature is self-efficacy. If an individual has a high sense of self-efficacy in financial matters, he or she have confidence to achieve financial goals and fulfill the financial responsibilities. Individuals that have a high self-efficacy evaluate their financial decisions more effectively and adhere to these decisions more consistently. At the same time, individuals with high sense of self-efficacy are more motivated when faced with financial challenges, and they use their skills to find solutions. And the last one is self-control. It's the ability to carefully evaluate financial decisions and managing spending habits. Individuals with high self-control usually manage their income wisely, and they keep their spending under control and pay their debts regularly. Therefore, high sense of self-control can increase creditworthiness, while low self-control can increase credit risk. And there are some more attributes that express creditworthiness, like impatience, emotional stability, impulsivity, self-confidence, and etc. In experimental results, in this study for testing the accuracy metrics of a constructed model, dataset has been split into training and testing datasets with 80 to 20 ratio. As I mentioned before, I use 5 different algorithms, and in this table you can see the metrics of these different algorithms. Except for the decision tree algorithm, all the other 4 algorithms have the same metrics, and all have an accuracy value of 0.9615. And we can say that model can predict the creditworthiness with high accuracy with these 4 algorithms. And although the accuracy value of a decision tree algorithm is lower than the others, it still has a high accuracy value of 0.923 and 0. And we can say that a decision tree algorithm can also used for this data set. As a conclusion, in this study, we examined the effectiveness of using psychometric tests in the credit lending process to measure customers' creditworthiness. We used several algorithms, and we compared the results, and we can say that psychometric data can be used to determine a person's credit risk with a reasonable accuracy. And also, it is also concluded that psychometric tests can increase financial inclusion by enabling customers without credit history or sufficient data to access to financial opportunities. And this was my presentation. Thank you for listening to me.
Thank you very much, Dr. Newman. Is there anyone who has Can you hear me now?
Yes, I can hear you now.
Okay, thank you. We're waiting for the questions, if anyone has any. No questions? Okay. Thank you very much, Dr. Dillman, and thank
So
you for sharing your work with us.
Thank you.
If the next speaker is ready, we can proceed. Next work is apply ANN to predict standard time in manufacturing, an empirical study of jewelry industry in Vietnam. Dr. Pham, are you ready?
Yeah, I'm ready.
Okay,
let
I
me
can.
share my screen.
Okay, I can hear you clearly. Okay, I can see your screen. You can start when you want.
Okay, thank you.
Thank you.
Okay. Good afternoon, everyone. My name is Quốc Trung Phạm. I want to present my paper with the title Apply ANN to Predict the Standard Time in Manufacturing, an empirical study of jewelry industry in Vietnam. I'm from Ho Chi Minh City University of Technology. So the content of my presentation today include 6 parts: introduction, literature review, case study analysis, research method, experiment and result, and finally conclusion and recommendation. So first of all, we know the jewelry manufacturing is a combination of manual process, which is highly dependent on skill level of operator. The planning and costing work faced with much challenge because the estimation of the standard time is not precise. Currently, the standard time is estimated by the starting point and completing point, which are used to produce a number of products in the jewelry industry. And in reality, there are some disadvantages that could be summarized here. For example, if production had any problem about the quality, the duration of the whole process will be attained. The data for a specific product is unpredictable at the first time. And if there is any change in technology, the time estimation must be changed. And the data is often fluctuates in different periods and not consistent in production. And the current approach is not good enough for jewelry industry because of the high error rate, about 20 to 50% compared with the actual performance of factory. So we need to find some solution to improve the accuracy. Moreover, we know about the artificial neural network. It is recognized as a feasible and cheap solution for solving the time prediction and production planning problem of various industry. However, there is a lack of application of ANN in the jewelry industry. So therefore, this paper try to propose a solution based on ANN to predict the standard time for the jewelry industry to have to improve the accuracy and consistent in production time. So the objective of this research include first to develop an artificial neural network model for predicting the standard time of the production process of the jewelry industry in Vietnam, and second to evaluate the proposed solution and to give suggestion for the implementation of the proposed solution in practice. So about the literature review, we know about the Thai study and its application in some industry. And Thai study had been studied a few decades ago, and the standard minute value had been calculated for its operation or job. Based on this technique, its operator capacity is measured and balanced to eliminate the bottleneck. There was some success in implementation of Thai study in some industry. first sample in 1994. It studied for the die manufacturing process using the multi-regression model. And in 2016, another research for using time study for the garment industry with the general sewing data code into the sewing garment industry. And in 2017, another research focused on improving productivity of garment industry in the Thai study. So also that the importance of Thai study in various industry. However, we want to know, we know the limitation of using Thai study only for the jewelry industry, so that we learn about the application of the ANN and its application. And ANN is a critical important baseline for machine learning programming, and there are various applications such as the spell checking, deepfake algorithm, voice recognition, and the most advantage of artificial neural network that can continue without any problem by their parallel nature when an element of the neural network fails. And we see there's some algorithm developed in the concept of ANN that could be included the multi-layer perceptron network and a general regression neural network. And the detail could be found in the full paper. And the performance parameter in developing the ANN network is very important to evaluate the accuracy of the model. And there are two error parameter that's very important to evaluate the ANN model. That is the mean wear error and the mean absolute error. That could be used the true formula on the screen. And the better artificial neural model network model should have the lower precision error in all of the training, testing, and validating. So now we move on to the case study analysis of the jewelry industry. This figure summarizes the business process of jewelry product development. It includes the development phase and the marketing decision. First, we have the 3D design. The product is designed in a 3D drawing, and then sample production and standardized estimation. The R&D team produce the sample. Industrial engineering have to estimate the standard type for this product. And then the cost of goods sold calculation. From the standard type, the cost of new product is calculated. And the next step is shipment. Ship the sample attached with the cost to marketing team. And then for the marketing decision, they have to make the decision whether to approve or not. If no, they will cancel the design. If yes, they can start the production of the final product. So look at the business process of jewelry production. We will see that the standardized estimation is done by copying the data from the similar product which had the same specification and same family with the developing sample. And the temporary first standardized is sent to SAP to calculate the quotation, and result will be forwarded to marketing. It's usually higher than the action cost, 30 to 50%. It's a hidden risk because many samples possibly stop producing after this phase become uncertain high cost. Therefore, it contains many wastes and risks inside. Secondly, the most important problem is how to forecast the size for the new jewelry production in the first time with accuracy about 90% or more. So in the future, the jewelry industry will increase the quantity of new products seasonally. In the fashion jewelry plan, new design sample will be submitted with the production cost of them, which is critically important to calculate the price of product on the market. The development task is conducted in several weeks, but the cost estimation task requires short duration within one day, a few days. Different from other industry, the Thai study only hardly reaching the accuracy because the sample production volume is smaller. In jewelry industry, the unit cost is high, and the standard Thai requirements should be close with mass production condition. Therefore, applying the Thai study and the artificial neural network model as a solution to predict the standard Thai for new jewelry sample could be a possible approach for solving the problem. So the research method, we follow the step by it to apply the ANN in the jewelry industry. The first step is define the input factor and output, and second step data collecting. The third step model development, and the fourth step compare and evaluate the model. We compare several models to choose the best one, and finally select the best model. So experiment design. In the first step, a team included experts working in this industry to brainstorm and identify the key factor for manufacturing, which directly consume Thai at its production process. Currently, there are no list of factors, so we need to interview with the expert. About the jewelry manufacturing, its operation must be depend on different factors. So the research only select one and two important operations to perform the ANN training and forecasting. In the next step, data from the history are collected and used to train the model. At least 10 different products are selected, involve 50 sample as raw data. In the third phase, the training data, testing data, and validation data are split and trained by different algorithms. There will be three alternatives to forecast the standard Thai. At the fourth step, the outcome from each alternative are compared, and the best model for forecasting is selected. The model will be expected to have the minimal error with actual standard Thai. So the result, by doing the brainstorm with the expert team, a lead up impact factor of vaccine activity, with a very important activity in the jewelry industry, including the mold quantity, the stone quantity, and the bean quantity. This can be presented in the figure below, including the three input factor, input layer, and then the heat layer, hidden layer, and the output layer in the standard Thai. And regarding to the model development, a software developed by the University of Adelaide School of Engineering is used for RNN training and validating. From data, we split the data set with the 60% for training, 20% for testing, and 20% for validation. This is just a normal way up split in the data set. After separating data set, we do train and test, apply the multi-layer perceptron algorithm. Because we don't have any guideline for learning rate momentum, so we try and select the best parameter with some option. Then we generate the four alternative, the two multi-layer perceptron algorithm model which have different parameter, and the two general regression the neural network which have different bandwidth, and the table here. So the final result and the comparison of the four alternative, MLB1, MLB2, GRNN3, and GRNN4. And the results show that we compare the error rest, mean square error, and mean absolute error. And the overall, all the artificial neural network model can rise to the low error in predicting. However, results show that the alternative 3 and 4 have the same result, and their error rate is lower than the other. So that we suggest to apply the general regression neural network number 3 and number 4 with the parameter here, and with the mean absolute error of training and testing data set achieved 2.9% and 4.5%. The capability of the model can satisfy the business owner. And in other aspects, the time to train and predict is quite short, so it's possible to complete during one day. So finally, conclusion. For manufacturing, the right estimation of production time can create the competitive advantage and maximize the profit, as well as the cut off the waste. From the analyzed result, ANN and GRNN can be considered as the good solution, which can yield the data from the actual performance to predict the standard time in a short period without spending too much efforts. The research had tested and demonstrated the accuracy of ANN model for predicting the standard time at vaccine activity. In fact, its operation in jury process had different input factors, so we need to apply it for all the activity. It's difficult to identify all of them at the first period. We not only need the expertise advice, but also the statistic methodology to evaluate the correlation between the input and output before selecting the input factor. The ANN, which use the MLB algorithm, can help the manufacturer to predict with 95% of accuracy with the collected data from 50 samples, which is acceptable for the current method. Besides, if there is any new implemented technique, we highly recommend that using the GSD code for trial test. At the time, ANN can well operate without training data, so the prediction shouldn't achieve the good point. Moreover, GSD code also provide us the standard motion process which is applied to standardize the manual work in jewelry manufacturing. Although the solution has been studied and demonstrated, there are some possible limitations. Firstly, we collect the data from fashion jewelry with the working condition in the specific 4M condition, man, machine, material, and method. So if there is any factor change, the input and data must be revalidated and tested before applying it. And finally, the acceptance level of the standard time affect the data collected. So in case the requirement for the accuracy is higher, more data should be prepared to train, test, and validate the ANN model. So the implication for future research will be develop a list of input factors which is suitable for jewelry industry and build it lead for developing the ANN model, and collect more data for training the model and evaluate the ANN model with different set of parameters to choose the best one. So that's all from my presentation. Thank you.
Thank you, Dr. Pham. Is there anyone who has questions for Dr. Pham? Please, you can proceed for some questions if you want to. Okay, very well. Thank you, Dr. Pham, for your contribution.
Thank you so much.
And the next presentation is now interpretable software defect prediction from project effort and static code metrics. And the speaker is the Dr. Alder. Is it correct?
I'm Shushmita Haldar. I don't have doctorate degree yet. Yes, I'm Shushmita Haldar. I'm doing PhD and a faculty.
Okay.
Thank you.
Well, if you are ready, you can proceed when you want.
Thank you. Good afternoon, everyone. Can you see my screen?
Yes, we can. Okay, you can proceed. Thank you.
All right, thank you. So good afternoon. The title of our paper is Interpretable Software Prediction, Defect Prediction from Project Effort and Static Code Matrices. My name is Shushmita Haldar, and so the author of this paper are myself, Shushmita Haldar, and Dr. Louis Fernando Capre. I'm from Department of Electrical and Computer Engineering, Western University, where I'm doing a PhD. And also I'm a faculty at the School of Information Technology of Fanshawe College. We are located in London, Ontario, Canada. The research objective. So here we can see from the pictures that the testers, their job is to test the application and find bugs. However, if they find if there are increased number of bugs even after the application goes to production, the cost of the software maintenance cost gets increased. So but the test managers are unsure of what to test. So what they want is they want to deliver the testing of the application within budget, scope, and time, but they're not sure what to test. What is the solution? Software defect prediction models can assist with the creation of test plans, and explainable software defect prediction models can build trust in the predicted outcomes. So here in the below picture, you can see that there is a task lead, and then they are actually collecting the data, apply machine learning algorithms on that data set, and then they can predict. This machine learning models can predict if that particular module is defective or not, and afterwards of course the test lead wants to have an explanation of the prediction. What are the challenges with this approach? It is quite used in the literature. Software defect prediction is a popular research area. But the limitations are there are limited information is available to test managers. SDP models may need to be created with minimal historical information. Unsure about which features to use as input, and the dataset may be imbalanced, which means the defect and non-defect ratio may not be equal or close. Lack of reliability in the created outcomes and unable to explain the predictions. Here is the background and the literature survey. So one of the solutions that comes into effect is a cross-project defect prediction. So available historical data may not be sufficient for training purposes, particularly when dealing with similar type of projects. So in that case, cross-project defect prediction involves leveraging data from different projects to predict defects in a new project. And here Chen et al., they have actually applied deep learning for predicting doing the cross-project defect prediction. Challenges with the cross-project defect prediction includes that there are variation of sizes, programming languages, development processes, etc. The next thing that we're looking at is also the explainability. So Gedzisi and Terhan, they have developed an interpretable SDP model using traditional model agnostic techniques of SHAP, LIME, and EL5. They applied explainable techniques to the gradient boost classifier model. So our research aim is to develop interpretable SDP models, software defect prediction models, using 4 different classifiers instead of 1 for comparability of explainability in different ML algorithms. Now, as I mentioned, that one of the challenge is the data is not balanced. So you can see in this picture or in this figure that, and this is actually taken from one of the data set that was used, that here you can see that the defective modules are only 30 instances. However, the non-defective modules are 108 instances. So in the past, like the SMOT, synthetic minority oversampling techniques, have been applied by researchers by Chawla in 2002, and that has been applied in other researches as well. Also, it is being popular in the software defect prediction research. So that can balance the data. So what happened is in that case, so it is matching with the majority class here. So right now it is 108 and 108 samples instead of 30 and 108. So that will tend to help us with the not getting bias towards the majority samples, which is the non-defective in this case. So we are in this paper, we are trying to give answers to the following questions. The first one is, can software defect prediction models generated from different projects with varied sample sizes yield consistent results? Does it significantly impact the results if highly correlated independent features are removed from the set of independent variables when developing software defect prediction models? Can we rely on prediction models developed using cross-project metrics compared to models built from individual projects? And can we consistently interpret software defect prediction models after applying smooth techniques to balance unbalanced data? Here is the methodology that we have used. So this is the data collection process. So we actually utilized the PROMIS data set that is from NASA. So here, and that has been, is a popular data set in research as it is publicly available. So we have selected those 5 different projects. You can see that they have C and C++ programming languages has been used, but you can see that the data is not balanced here because defect ratio is only here, let's say in CM1 project is only 9.8%. Here is the methodology that has been used. So we started with the data set, we loaded the data, we did of course, the exploratory data analysis, we cleaned the data, and then we did the feature selection, we balanced the data using smooth, we standardized the data. Afterwards, the data definitely has to be split between training and testing. We picked the 70% and 30%. And then split, and then we built our models with machine learning algorithms and feed models with training data. We applied hyperparameter tuning with threefold cross-validation, the optimized SDP models, and then we evaluate the SDP models with testing data. Afterwards, we applied the model agnostic techniques for understanding model and predictions, and then the SDP models have been deployed. I'm not going through each of these attributes because there are many, and it is also mentioned in the paper. So again, this has been taken from the PROMIS dataset that has actually different source code matrices and effort matrices. So you can see some of that will be highlighted here is, of course, the line of code in the program that we have. The other thing that was of interest is E, which is effort. So Halstead effort refers to the mental effort required to develop or maintain a program. So let's say if we have give less effort, are we going to have more defects or not? So the VG is the make-cap is cyclomatic complexity. So you can see that like how many blank lines of code we have, how many unique operators, unique operands, etc. And the defects, we are actually, this is our the predicted variable that we will be looking at. Is it going to be either false or true? Is it either defective or non-defective? So we did the data pre-processing, and here we started with cases with missing values. So we dropped them or we removed them from the data set. We looked at what are the cases that are implausible or conflicting feature values. We removed the outliers, especially that are in the Q1 and Q3. The first and third outside the range of third quartile and first quartile, and then the removal of the duplicates. So some of the instances had duplicates, so we removed them. And then finally, we actually used 2 approaches. So the first approach, we kept the highly correlated features in the data set, and the other approach is where we remove the any highly correlated features that are more than 70% highly correlated features. We remove them from the program or from the data set. So here is the data rebalancing and feature selection. So you can see that each of the projects have been rebalanced to meet the majority instances. So here you can see this example I showed earlier, 30, 108 became 108 and 108, which means you have 108 defective and 108 non-defective models. And we applied the same thing for all the projects. And this one is CP, which is we are also looking at the cross project. So what we did is primarily we added all those, we combined all these individual projects into one data set for doing the cross project effect prediction. And then here we, after applying in the second approach where we remove the highly correlated features, here you can see that different projects had retained different number of features because not all of the data sets were same. So this is what we ended up with. So here we applied the 4 of the common traditional techniques for machine learning techniques for the defect prediction. And then these are support vector machine, k-nearest neighbors, random forest classifiers, and artificial neural networks. And the details are also available in the paper. And then this is more interested, we were more interested in also in the explainability. So here you can see that we have applied SHAP and LIME. So LIME is actually a local interpretable model agnostic explanation, and that was initially introduced by Riverio et al. On 2016. So what LIME does is it builds sparse linear models around each prediction to explain how the black box model works in that local vicinity. So basically, in this case, we can go and see any particular observation. We can go and see why it predicted that particular outcome. So it's more for the local interpretability. The SHAP, it corresponds to the idea of Shapley values for model feature influence scoring. So that was actually built based on the game theory, and the Shapley value corresponds to the average marginal contribution of a feature value over all possible coalitions. So here that was developed in 2002, and this has been 2017 by Landerberg and Lee. Okay. So here we also used the traditional approach, a commonly used approach for evaluation of our defect prediction models. So accuracy is the percentage of correctly classified results. So accuracy is defined by the true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So we measured our accuracy, as well as we also look at the ROC AOC score, because we also wanted to make sure that because the data was imbalanced and we applied smooth, so we also focused on the receiving operating characteristics curve. Here is our result, and you can see in this picture that it has 2 sides. So in the top part, we have projects with 20 common features, so majority of the features were capped. However, in the bottom part, we have projects with the selected features where we have reduced the features based on the high correlation between the independent features. Here in the right side, I have listed the project name, the features, and then the clean samples. So you can see that the KC2 is the smallest number of records we have in the dataset after the cleaning was applied. The next one was CM1, PC1, and all of them don't have the similar number of features. And the CP stands for the cross project. So here we can, the way the yellow color, the highlighted ones, corresponds to the highest ROC AUC in each of these algorithms. So there is a possibility that we have higher accuracy, but if the ROC AUC is low, compared to the other methods, we are actually not considering that as the best classifier. So in this case, let's say the KC2, you can see that the accuracy is 73% and the ROC-AOC is 69%. And in this case, in the cross project, let's say the accuracy is 73%, but the ROC is 58%. However, you can see that in the cross project case, this random forest has a higher accuracy, which is 82% compared to the 73%, but still we are considering this as our ANN as our high performing one, because the ROC-AOC is higher, slightly higher than the other one. And this is, and also for each of these projects, we have taken the average score. So basically we took like each of these independent projects, and then we took average score for the accuracy and ROC-AOC to be able to compare it. So here our first research question is, can software project defect prediction generated from different projects with varied sample sizes yield consistent results? So the response to here after our analysis is the predicted models provided consistent results with slight variations depending on the sample size and selected features. So again, we can see that for the probably the smallest one like KC2, the KNN is working great. However, for the CP, the cross project, in both cases with all features and reduced features, the ANN is working great, is better. So the smallest dataset project KC2 and the KNN model performed the best in both feature selection approaches, but the CP yielded good results for the ANN classifier, as deep learning models tend to perform better with larger datasets. It was observed that there were trade-offs between accuracy and AUC. The second questions that we have is, does it significantly impact the results if highly correlated independent features are removed from the set of independent variables when developing software defect prediction models? It was found that this removal improved the average ROC-AOC score for SBM, KNN, and RF models, random forest models, with a slight decrease in the ANN model. So if we look at this one, so the removal improved the average ROC-AOC score. So you can see here is the 20 common features, and here is the reduced features. So if we see here, the average ROC-AOC score for the SBM is 59%, but in our case, with the reduced features, it is 60%. So it is slightly better, although in the ANN model it got a little bit decreased. But there is no not necessarily there is a decline in the performance, decrease in the performance. So that it was found that removing correlated features had varying effects on model performance, but did not significantly alter the overall outcomes. The third research question was, can we rely on prediction models developed using cross-project metrics compared to models built from individual projects? And it was found that the CP models perform slightly lower than the individual project's average performance. However, the performance did not go down drastically, and they are very close to the average score. So the ANN model with reduced feature shows the average accuracy and AUC score was 76% and 61%, whereas the cross-project model had an accuracy and AUC as 70% and 61% respectively. So CP, that means although it can reduce the performance a little bit, but we are saying when there is when the historical information is not available for CP, for similar projects, CP is still a good option. Then here we also looked at the interpretability. So this is when we kept all the features, and this is a figure from the after applying SHAP on the ANN model for the cross project. And here it is after reducing for the same cross project model, but here we reduce the features, highly correlated features. And you can see here that is some of the features that are, we can see that for the prediction here, the line of code is, how many line of code is in the program is paying a significant amount of contribution. Then it is the cyclomatic complexity, etc. Here, because we removed all the features, we have kept all the features here. We can see that the line of code is also an important feature. It's probably not the best one, but it is in the 4th position here. Now, for this same SHAP model, we also applied in the reduced feature, we picked a particular observation. So this SHAP model is on total 20 observations. This LIME has been applied on a single prediction, a single record, and we can see here that is still for this one, it is 71% probability that this is not defective. But for not being defective, these ones paid contributed. So the that means the VG is less than a certain amount. So the cyclomatic complexity was low here. So that's why it is going towards not being defective, and so on here. Now, this is another example that we have taken on the with a LIME and SHAP here. So here you can see that in another model we have applied, and then you can see this is a single observation, and here we can see that the line of blank line is greater than a certain number. So it is showing that it is going towards not being defective. The effort is greater than a certain number, but less than this, so it is going towards being defective. And then so on. So here we have length, line of comments, line of code, etc. Here, if we look at the right-hand side, this is the SHAP again, and this is again on the 20, the number of observation here are 20. And here we can see that the effort is the most important predictor here. And then we have the length and the blank line of code. So which is kind of aligning with this here. So we have the blank line of code and effort, although here we are looking at more than a single one, so that slightly got changed. So both SHAP and so our the research question was, can we consistently interpret software defect prediction models after applying smooth techniques to balance unbalanced data? So both SHAP and LIME successfully explained the predictions, providing insights into the contributing features. So the conclusion and the future work is this study developed software defect prediction models focusing on interpretability using individual projects and a cross-project dataset. Removing highly correlated features during comparative studies did not significantly compromise the performance in the cross-project defect prediction model, although individual projects' average scores generally achieve better results than cross-project scores. Hence, when historical information for similar project is not available, cross-project defect prediction is a viable option. Model agnostic techniques like SHAM and LIME demonstrated unbiased predictions after applying data rebalancing. So we also wanted to see, after applying smooth, if we could still explain the prediction. Local predictions had slight differences from global predictions due to individual records and features contributing differently. The study suggests that the source code and effort metrics can be important for defect prediction. In the future, there is more room for research to be conducted on applying principal component analysis and other methods to tackle multicollinearity issue and consider their impact on interpretability. So if you have any questions, thank you so much for listening to this presentation.
Thank you very much, Ms. Haller. Are there any questions from the audience? No question? Okay. Thank you very much, Ms. Haller.
Thank you so much, Mark.
So, a warm greeting and sincere thanks to all of these afternoon speakers for the session. We all particularly appreciated your work and your presentations. We hope you are satisfied too and that you want to participate in the next edition in 2024. Thank you again and have a good day.
Thank you very much. Good day.
Thank you so
very
much.
Thank you so much. Thank you. Goodbye.
Goodbye.